That's great to have people here. Can people see the screen? Okay, let me.
Yeah.
The slide.
Better?
Yeah, for me it's better, but I don't know. Probably what matters is the audience. Even if I cannot see anything, you all should be. Okay, great. Okay, it's great to be here. It's surprising that this is actually my first real time in Colorado. Not even at a university in the state itself. I've been to the Mesa Verde National Park driving from one of my internships, but never to the Rockies or this area. It seems very similar to Switzerland in many aspects. Yeah, thank you. Yes. Yeah, thanks. So I'm going to talk about something that's we've been working on for more than 12 years now, RowHammer. It keeps getting, whenever I think about not working on it, it keeps getting more interesting. So hopefully it'll be interesting to you too. And I should also say that I have lots of slides. I have a story to tell, but we don't need to go over every single detail of what is on the slide. So feel free to ask questions about things. So this talks about robustness. And when I actually teach the freshman digital design and computer architecture class at ETH, and I actually put this picture in the first lecture and talk about the infrastructure that these people who are taking the class are going to build into the future. And when we talk about infrastructure, human beings have been building infrastructure for thousands of years. And this is an example of infrastructure. How many people know this bridge?
It's the one in Seattle?
Yes. Yes, Tacoma Narrows Bridge. Yes, there you go. So you took a good freshman class. So this is the Tacoma Narrows Bridge. It doesn't exist anymore because a Bitflip happened to it. Well, it's not a Bitflip. You can learn about what really happened to it, but it's a reliability problem, essentially a robustness problem. And after this happened, people started building bridges using wind tunnels and wind tunnel simulations, etc. So it actually enabled a better way of designing systems or infrastructure. I also use this picture. People are building this beautiful city over here, and they trust this infrastructure that they're sitting on. They wouldn't be trusting this infrastructure if a Bitflip happened soon after, right? So I think of robustness. I wrote security over here, but I think of robustness as preventing unforeseen consequences in the end, because we will be building a lot more and bigger infrastructure than this. And it's already happening, right? Our computing devices are everywhere, and they're going to be even more everywhere. And this is one example that I use. This is Mr. Bean and his envisioning of the self-driving car. He trusts his car, but I'm not sure if we should trust our cars unless we actually design them in a very robust way. Okay, why am I telling you all of this? Because basically we have Bitflips in existing systems today, and they're all everywhere. Essentially all DRAM chips. DRAM is the main memory that's used for building memories today. All DRAM chips are vulnerable. You can induce Bitflips in them. And also RowHammer is the first example of how a simple hardware failure mechanism can create a widespread system security vulnerability. And if you know of something else, please let me know. Then I'm happy to change this claim over here. But so far, I haven't found anything else. And people are actually writing articles like this. I like this one, especially when people question, okay, why are we studying digital design in a freshman class in a computer science curriculum? Well, other people are also interested in it, as you can see, right? Forget software. Now hackers are exploiting physics. Some interesting articles. Okay, so let me give you the backstory a little bit. We've been working on memory for a long time. And this is, we've always argued that memory will become a much bigger problem in systems in many dimensions: performance, efficiency, energy, but also robustness. And we've always argued that we should not really try to treat memory as memory, but we should really try to treat memory as part of the system and co-design the system together with memory. This way we can much better scale the system as opposed to scaling the technology itself. And I'm going to hopefully give you examples of how we can get there. Okay, we're going to talk about DRAM. DRAM is the technology that's used to build essentially all memories today. If you're building a computer, if you have a computer, you have lots of DRAM. Everybody here has lots of DRAM. And DRAM is a charge-based memory. You store charge in this capacitor, and you need to access that charge using this access transistor and some sensing circuitry over here. And for this memory to work, both the capacitor needs to work well, and the sensing structures as well as the access transistor need to work well. Now, when you reduce the size of this circuit to essentially store more data per millimeter square, it becomes very difficult to maintain the reliable sensing and reliable storage properties, because this structure, capacitance becomes very small, and the sensing becomes much more vulnerable to noise. And these cells start affecting each other. And we're going to talk about that essentially. And this is actually a more real picture of how these cells look like. This is the capacitor over here. It's really etched into the device in a 3D manner, and the access transistor is next to it. So people are actually developing a lot of innovation at the very low levels to make these much more scalable. And even then, we're having problems. Okay, so we were actually very interested in these memory errors for a long time. We did the study with Facebook at the time, around 2013. We spent 1.5 years or so. We studied essentially all of the memory errors that they have in their data centers. It's actually fascinating. They have some of the huge infrastructure at the time, and they didn't allow us to publish how big their memory is, how big their data centers are, but they did allow us to publish some conclusions. So this was one data point we published. Essentially, this shows that in production data centers, the density of the DRAM chip that's employed correlates very well with the failure rate that you see in the systems. Meaning that the denser the DRAM chip that you employ is, the more servers are failing. This is because you get more memory errors in denser DRAM chips because cells are smaller and cells are closer to each other. So this is one effect of what we see. And there are a lot of actual papers on this topic, which is quite interesting, but I don't want to go into it. This is one paper. It's been a while, as you can see. So while we're doing these studies, we also wanted to ask the question, can we really identify the failure mechanisms in DRAM so that we can really do something about it? The previous study that I showed you was not a controlled study, right? We basically observed all of the errors that are happening in production data centers for some time. Can we really control things so that we can understand what's going on? So we built these beautiful FPGA-based infrastructure. This is around 2011. I'm going to show you more recent pictures as well. We have FPGAs, and we can actually change the memory controller. We have essentially a soft memory controller where we can change the commands that we send to DRAM and their intervals, their latencies, so that we can test DRAM. For example, we can turn off refresh. And that's actually the main reason why we built this infrastructure. I will talk about that very briefly. These are more recent. Actually, a lot of the studies that I'm going to describe are done in this infrastructure. And we've open sourced this. People have been using it in both academia and industry. We've been supporting them. If you're interested in using it and doing research in this topic, we'd be happy to support it. Just don't use this one. Use the more recent one, which is actually much better, I would say, more easily programmable. And it's also ported to many different FPGAs. Unfortunately, we don't provide the FPGA. You need to buy that yourself, but all of the software is open source. Okay, so the reason we built this infrastructure was to understand the scaling problems. And one of the scaling problems at the time, we're talking about 2010, we were thinking about this data retention. Because fundamentally, charge-based memory needs to retain data. And if it cannot retain data, you need to refresh it. And none of these memories retain data for long, so you need to refresh them. So for example, the cell phone in my pocket is refreshing its memory right now, wasting energy. And we wanted to ask the question, can we understand the fundamental properties of this data retention in memory so that we can get rid of refreshes as much as possible? And this is what we knew at the time, but we wanted to measure and understand it. So basically, if you measure the retention time of cells in DRAM, it looks like this. It's a distribution. Because of process manufacturing variation, some cells can retain data for long. A small fraction of cells cannot retain data for long, and you need to set the refresh rate so that you actually get correctness for all cells. So if you know this picture, you can actually verify it using the infrastructure that we did by turning off the refreshes for long enough times. And you can understand this properties. Now, I'm not going to get into this. Yes, please. If you want to get into this, go ahead.
So did you guys notice that the cells that did not support lower refresh rates were near each other, or were they sparse? Like
It's all randomly distributed.
All randomly
Yeah,
distributed.
it's mainly random process variation, essentially.
Okay.
Yes.
All right. So that's the reason for the differences.
Exactly, yes.
Process.
Mainly process variation, yes.
Okay.
I'd be happy to talk about more. We have a lot of data published in the papers, yes. So essentially, the retention time of a cell is, we wanted to get rid of refreshes. If you actually understand this picture, you can design a memory controller that refreshes cells at the rates that they're really supposed to be refreshed at, as opposed to using a single rate, which is what we do today. Today, we actually refresh everything every 32 milliseconds. But this turns out this is not an easy problem. It's actually much harder than it looks because it's not just dependent on the location. It's also dependent on the value stored in the cells, the retention time. And the retention time is also dependent on quantum-like effects that you cannot control. It's quite random, actually, in some cases. So it's actually a very difficult problem. And we publish papers that talk about this. I'd be happy to talk about that separately. So this is one of the scaling issues in DRAM. It's not easy. And this is one of the things that keeps DRAM manufacturers up at night, I would say. But there's another issue that we later started studying. And this is RowHammer, essentially. So what is RowHammer? I'm going to give you a high-level picture. I'm not going to go through the device level as much in this talk, but I'd be happy to talk about it if you want. I'll draw an abstraction level. So all memory consists of rows of cells in the end, and DRAM looks like this. Essentially, it's a two-dimensional array structure underneath, and you have hierarchy of these array structures. If you want to access some cell, let's say a bit in one row, you need to activate that row, which means that you apply high voltage to the word line to enable the access transistors that I showed you earlier in that entire row. This could be 8 kilobytes, for example. Now, you can access the cell that you're interested in by issuing a read command afterwards. Now, if you want to access some other cell, you need to close this row, meaning apply low voltage to that word line. This is also called a pre-charge in DRAM. And if you keep doing this repeatedly, open, close, or activate, pre-charge, activate, pre-charge, activate, pre-charge, activate, pre-charge, enough times, it turns out cells in physically adjacent rows get corrupt. They leak charge, and they leak enough charge at some point, because you do these activations many times, that they lose their data. Now, clearly, this should not be happening, right? Because we're not even writing to memory. We're just reading, activating a row. We should be changing nothing in memory, let alone rows that do not even belong to us potentially. This could be belonging to some other application, the operating system, or even your application, and maybe some critical data. So we call this the hammered row. We call this the victim rows. And we showed that at the time, based on our testing procedures, more than 80% of the chips that are manufactured by 3 major DRAM manufacturers are vulnerable. There are only 3 major DRAM manufacturers in the world that occupy more than 96% of the DRAM market. Okay, I'm not going to name them at this point, but you can guess who they are, right? Okay, so we argued that this is a technology scaling problem because we did not see this effect in modules that are manufactured before 2010. The first occurrence was 2010. And every module that we tested that was manufactured between 2012 and 13 was vulnerable. Okay, so why is this happening? I think I've already kind of given the high-level picture. DRAMs are essentially too small and too close to each other. They're not electrically isolated from each other. There's electrical interference between the cells and the wires. And this is also called cell-to-cell coupling interference. And if you know about memory, this is nothing new, right? Because as people design memories, there's read disturbance. Whenever you access one cell, you're interfering with some other cell. And this is very well known in flash memory. I'm going to talk about some pictures. And that's one of the reasons why we want to study this problem also. There are actually multiple underlying factors in DRAM. Different memories have different read disturbance effects. In DRAM, there are multiple underlying factors. I'll give you one factor over here. I'd be happy to talk about other factors as well. So at a high level, when you activate or apply high voltage to a row, an adjacent row slightly gets activated as well because you don't have enough isolation. And vulnerable cells in that adjacent row leak charge a little bit. And if you do this hammering, activation, pre-charge enough times, you basically deplete the charge from those vulnerable cells, assuming you can do enough activations before the cells get refreshed. Which means that if you actually refresh DRAM much more frequently, you can prevent this problem. But remember, we don't want refreshes because they waste energy. And actually, we wanted to get rid of refreshes to begin with. So this is going to be very fundamental. To get rid of RowHammer, you can actually exacerbate some other problem in DRAM, which is refresh. Okay. Okay, so this is, as I said, this is nothing new from a general memory perspective, but the understanding is necessary so that we can solve these issues. And one of the really interesting things in DRAM is if you get these Bitflips in real chips, and if you can induce them using user-level programs, then this is immediately visible to your programming language, right? Because your data structures are DRAM, so your data structures get corrupt. And there's nothing to fix that in DRAM today. Modern memories don't have enough error protection for that, as we will discuss later. Okay, so we did actually do this. In the paper, we also showed that you could actually write a very simple user-level program that looks like this, which selects addresses X and Y such that they go to different rows in the same bank. It also bypasses the caches and bypasses the row buffer in DRAM. And basically, ping-pongs activates to X and Y. And if the chip is vulnerable, hopefully you'll get Bitflips. You can actually download this program and try it on your computer. Just don't do something really important, maybe. Actually, even better, there are much better programs today in 2022. Google built on this work, and they actually released their program, and there are even better ones. So one realization over here I will mention is if you select X and Y carefully, such that there's only one row sandwiched in between, you exacerbate the interference much more. This is called double-sided RowHammer, and you get the Bitflips much earlier and many more Bitflips. We showed that in the paper, but we did not study most of our effects. So I think this actually increased the vulnerability of DRM a lot more. Okay, yes, please. Excellent question. It does depend. And we actually have a DSN 2022 paper that I'm going to mention later on. If you reduce the voltage, you get less of an effect as expected. But it doesn't completely get rid of the problem. You have to reduce the voltage so much that latencies have to increase a lot and retention becomes a problem. So it does depend on the voltage.
You reduce the voltage, you also storing less charge.
That's correct, yes. Exactly, you may be exacerbating the latency and retention problem. But we did study this scientifically so that we can understand if there's a better operating point. It's a very tough operating point, in my opinion, but it's a great question. So we show that this program actually induces bitflips in real systems, Intel and AMD. There's nothing specific about the Intel and AMD. As long as you can build a memory controller that's good enough, which all memory controllers should be today, you can actually induce these bitflips. Okay, so when we wrote the paper, we started the paper saying that this should not be happening, basically. We said that memory isolation between different cells is a key property of a reliable and secure computing system, and access to one memory address should not have unintended side effects on data stored in other addresses. I think this is really critical for robustness. And we said in the paper that someone can take the program that we wrote and build an attack on top of it. This could crash your computer, hijack your computer, do all sorts of bad things. And while we were doing some of that, these good folks from Google Project Zero published a blog post, which essentially showed what we suggested. And I think this is fascinating. If you're interested in system security, I would definitely recommend reading their blog post. They also have a black hat presentation. I copied and pasted part of their blog post over here. They basically read our paper and they replicated the problem based on our paper. And they built essentially two attacks. One of them takes over the Google native client. We're going to get back to that at the very end of the talk. Hopefully I'll get there. The second one actually is very interesting. They were able to induce bitflips in page table entries of a user level process while just running this user level program. And this user level process was able to flip bits in its page table entries that point to its own page table. As a result, they were able to gain write access to their own page table using this user level process. Now, once you have write access to your own page table, all bets are off. You can do anything you want, right? Now, it's not an easy attack. It's a probabilistic attack, and they actually built something called page table spraying. They had to fill the memory with a lot of page tables so that they could increase the success of the attack. But I'm not going to go into the attacks as much. I just recommend that you take a look at this paper, a black hat presentation if you're interested. There was a question in the back? Okay. Okay. So this became famous as the RowHammer vulnerability, and I like some of the analogies that people have written. This is from a famous hacker on the internet. He basically said that RowHammer is like breaking into an apartment by repeatedly slamming a neighbor's door until the vibrations open the door you were after. So if you're stuck in this room and all doors are locked, don't worry. The emergency exit doesn't work, don't worry, keep banging on the wall. If RowHammer effect is in effect, if you will, then hopefully the door will open. Okay, so this should not be happening, as you can see, right? You could argue that you don't want to escape from here also. That's another security feature. Okay, so people built a lot of attacks on top of this. I'm not going to go into the attacks in this, but these folks from TU Graz showed that you could actually take over someone's computer remotely by inducing these bitflips through JavaScript. This is a beautiful paper from VU Amsterdam, where they actually released an app. And in this app, they were able to figure out which parts of your memory in a cell phone are vulnerable. And they exploited the deterministic memory allocation properties of the Android operating system at the time to fool the operating system to allocate a page table entry of the user level process into a location that they knew is vulnerable to RowHammer, and they would actually take over your system. I don't know if their app is still downloadable. I don't use Android, so you can take a look if you're interested. People showed that you could actually excite these attacks using GPUs. You could do this through remote direct memory access engine in a remote computer, and these folks also showed that. Even if you cannot take over some other computer or this computer, you could actually break confidentiality. These folks showed that by using RowHammer, inducing RowHammer bitflips, by exploiting what is called data pattern dependence that I will briefly talk about, you could actually identify private data that doesn't belong to you. This actually changed the game a little bit. So RowHammer became also a confidentiality attack as opposed to just an integrity attack. More recently, people have been also looking at neural networks, and people have been writing papers. These are just a selection of papers. Sorry if I haven't covered your paper, but there are many papers in this area. So people have shown that, for example, if you're able to do some of these RowHammer attacks in a relatively intelligent manner, you could turn a reasonably accurate neural network to a completely useless one, essentially. And there are more of these works. I'm going to talk about this later on. Industry has been also developing both attacks and solutions. We're going to talk about that, which is interesting. Google has been writing both attack papers as well as solution papers that we will see. So there are people have been drawing interesting pictures like this also. This may be a solution to RowHammer. I wouldn't recommend it. This may be an attack also, as you can see, right? A different kind of RowHammer attack. So we've been writing a lot of papers. I'm going to cover some of the things that we've been talking about. And even some of the overview papers that we've written are out of date right now. We need to keep updating it. So now I'm going to talk about understanding RowHammer a little bit, because that is required to build solutions. And then I'm going to talk about solutions. I'm going to switch between understanding and solutions a little bit in this talk, just to give you a history of what's been happening as well. Yes?
Good question.
Sure.
Arvin is saying, I know you said you were not going to dwell at the device level, but is it possible to protect against RowHammer by trying the adjacent rows down to the opposite rail voltage? This is probably already being done, but wanted to.
Yes. So the short answer is no. And yes, people have already tried a lot of those tricks, but it doesn't work. Yeah. Maybe we'll leave it at that for now. Okay, any other questions? Otherwise, I'm going to jump into understanding. And depending on how much time we have, please feel free to stop me if we're going too long. Probably we're going too long, regardless. Okay, understanding. So in our paper, we wanted to build a scientific understanding of this work. And that's why we actually enhanced our infrastructure. We tested lots of modules, more than 120, as you can see. And we built some understanding. I'm going to discuss some of these over here. So one of the things that you want to understand in this case is, from the memory controller's perspective, where are these rows that are being hammered, if you will? So if you have an aggressor row and if you have a victim row, what is the distance from the memory controller's perspective? And I'm emphasizing this memory controller's perspective because when you have addresses in the memory controller, those addresses do not necessarily map to physical addresses inside the DRAM, because DRAM actually does some address remapping internally to maintain reliability and other things. So this is what we found. Essentially, from the memory controller's perspective, most of them were adjacent, but there were some non-adjacencies because internally there's some remapping that goes on inside DRAM to protect against faults, etc. Meaning that memory controller cannot assume that victims and aggressors are adjacent. Meaning, one of the solutions that we're going to discuss is, for example, whenever you access an aggressor row a lot, refresh the victim rows. Can the memory controller know the victim rows? And the answer to this is no, unless you have further information. Okay, so it's going to be difficult to build defenses from the memory controller perspective. Okay, let's take a look at access interval, meaning what if we don't access memory as frequently? We reduce the access interval to different rows. How much should you reduce? And at the time we were testing, the minimum was 52.5 nanoseconds between two activates. In order to get rid of every error that we saw, we needed to increase the access interval to 500 nanoseconds. Now, this is very bad because this actually increased the latency to memory that people are trying to reduce as much as possible. So this is not a good solution unless it's applied very, very selectively. And we're going to talk about that very briefly. I believe very selectively applying throttling of accesses, meaning reducing the access interval between two different activates, is important. Okay, refresh. Let's talk about refresh. We wanted to understand how frequently you need to do refresh DRAM to get rid of every error that we have seen. And the answer is you need to increase your refresh rate by 7x to get rid of every single error we have seen. And that's probably bad. Hopefully, it's clear right now. And I should also mention that we did a lot of these studies with single-sided RowHammer. With double-sided RowHammer, those numbers increase much more. So this is not a good solution, we argued. This is interesting, data pattern. So a data pattern actually affects the charge coupling between different cells. So this data pattern on the right induces a lot more charge coupling. As a result, you get a lot more errors due to RowHammer. Okay, there are a lot of other observations in the paper that I will very briefly talk about. Errors are very repeatable. These are very different from retention errors, actually, because the error mechanisms are different. Simple error correcting codes do not correct all of the errors that we see. We're going to talk about that later on also, because we get a lot of errors per cache block or code word, ECC code word. And we already talked about double-sided hammering. So I'll just summarize the earlier paper to you. We have actually developed a lot more understanding over the years. I will talk about some of these in a little bit before, but I want to switch solutions. It's getting much worse. It has many dimensions. Voltage is very important. it's HBM chips are also very vulnerable. People are building huge AI infrastructures with HBM chips today, and they're as vulnerable, and there are other effects in HBM chips also because of the three-dimensional stacking. And spatial variation is important. But I will talk about some of these later on. Let's talk about solutions, since people usually tend to become interested in solutions very quickly. How do you solve this problem? Well, if this were a class, probably we would be having a discussion, but I'll probably give you the high-level overview. So if you discover a problem like this, basically you have a problem in the field because there are chips that are vulnerable in the field, and you have not designed your system to protect against it. What do? There are limited possibilities if your system is not flexible. And I'm going to argue that you need to have better memory controllers to make your system flexible going into the future. But at the time this was discovered, memory controllers were not flexible. They're a little bit more flexible right now, but still quite rigid. Longer term, you have a lot of creativity that you can come up with, and people are still coming up with a lot of solutions to RowHammer. I'm going to talk about some of these solutions as well. This is one slide that summarizes a lot of the solution approaches. It doesn't include all of them. The first one I'm going to dismiss. Essentially, it's very difficult to build more robust DRAM chips. You can use different materials, for example, that are less vulnerable. You can put isolation between the cells. You can have better error correcting codes. A lot of them are very costly in the end. You need a huge amount of cost. You can increase the refresh rate. This is very costly also, as I've shown you earlier. Physical isolation is very interesting. You can put some physical isolation between rows inside the memory controller or the software operating system memory allocator. Very interesting, but also expensive. Basically, you waste a lot of memory by doing so. I think we're left with two solutions over here. I don't have remapping solutions over here, but I'm happy to talk about that separately. Reactive refresh, meaning identify aggressor rows somehow and refresh victim rows, potential victim rows, or identify aggressor rows somehow and throttle accesses to aggressor rows so that you don't induce bitflips in victim rows. I think these are two nice directions. Yes, please.
So, is it possible that you can go to a solution that doesn't even involve VNAND and instead work with a different type of high density memory, like phase change memory or something like that? And get rid of all these inherent problems that DRAM has by going to a completely different memory technology?
I mean, that's an excellent question. And actually, I have worked on phase change memory a lot myself, also flash memory. Unfortunately, all scaled memory technologies have this sort of noise issues in the end. Electrical interference is something we cannot control, whether something is charge-based or resistor-based. And people have shown actually in simulation attacks on STT-MRAM, for example, and also phase change memory. It's not exactly the same in nature, but in the end, there's coupling. There's cell-to-cell interference that's happening in these memories. You can get rid of some of the other problems like refresh or increase the refresh intervals very large, but interference or disturbance effects are very hard to control. But that's a great question, I think. That's one of the reasons why we wanted to also look at phase change memory. Yeah. Yes. That's an excellent question. In the end, I believe they have to be hardware activated because the number of activations you need to do today to these bitflips are very low. So the software is very hard to control, I think. But I think they need to be hardware software cooperative because hardware cannot take all the mitigating actions, in my opinion. Once it detects, it needs to inform the software. That's what we've been arguing. It could potentially, so if the software is able to, for example, profile and understand an attack is going on at a very fine granularity, if you have that interface from the software, I think you could also do it in software. The problem is we don't have that interface from the software today.
In the end, it's
Exactly. Some sort of profiling, essentially. Okay.
I have a question about that. So you said that in your opinion, the hardware should not be alone in defending against attacks, but why? I mean, it seems to me like the natural course of life that, if you have this problem in the memory device, the defense should be in the memory device, since it has like kind of knowledge about everything.
That's can I hold on that one? I don't think the memory device has knowledge about everything. I think it needs to be discovered.
Like
the memory system, maybe. Yes. I think the issue becomes in the end, what happens if you detect something, right? What do you do? At that point, I think the hardware has limited possibility. It needs to bump to software. Or software, I think this program is doing something fishy, let's say. It's attacking this part of memory. Figure out what's going on. I think that hardware cannot do, in my opinion. At least from that part, I think there needs to be some action. But let's talk about whether the memory device can completely do it itself, because this is fascinating, I think. It's a scaling problem that's really affecting everywhere
Yeah.
in the system. So, okay, I should mention that basically we don't have a great solution, in my opinion, yet. Everything is a trade-off between cost, power, performance, and complexity. And if you're willing to trade off robustness, you could actually add robustness over here too, because it could be a bit error rate thing also. Okay, so what did industry do? Industry basically increased the refresh rates. Why? Because that's the only thing they could do. And this is Apple's beautiful patch where they discussed it. They basically said this issue was mitigated by increasing the memory refresh rates. They didn't say how much. I believe 2x. And as you've seen, 2x is not enough to get rid of all of the errors. And I like Apple because they actually reference the academic works that lead to it. Industry should always do this, I think, whenever they actually do something based on academic works. Okay. So our solution, this is the solution that we argued was best at the time. This doesn't work alone today because RowHammer thresholds have reduced a lot. So at the time, just to give you an idea, at the time, we were able to induce Bitflips by doing 139,000 activations, single-sided. Today, I'm going to show you one paper very quickly. I'll go over that probably since it's better to take questions. You could actually induce Bitflips after only 4,800 activations. So the problem is getting much worse over a decade or so, maybe 7 years or so. So at the time, the solution worked. The idea was very simple. I still like the basic idea over here. It's a probabilistic approach. Memory controller, after closing a row, it activates one or both of the victim rows, assuming it knows them, with very low probability. Now, this gets rid of the RowHammer problem because your reliability guarantees become much better than what is expected of DRAM. And if you're paranoid, you can actually adjust P, the probability, to increase the strength of protection. And this is one of the beautiful things is this is low cost, it's stateless, low complexity, and low overhead at the time. And you could actually do this in the DRAM chip. Part of this idea is implemented in today's DRAM chips in a broken manner. I will mention that. You could actually do this in the memory controller, which we argued for, but the memory controller needs a little bit more information. And Intel actually implemented, one of the first solutions to RowHammer was implemented in Intel memory controllers. And they actually implemented a version of this idea in the memory controllers. And in the BIOS, it's not exactly how we envisioned it, but in the BIOS, for example, you can control it. You can choose your hardware RowHammer protection versus or 2x refresh. And if you choose your hardware RowHammer protection, you're given a range of possibilities. Which probability do you want to choose? Do you want to activate every other activation, or do you want to activate every 2 to the 15th activation? That's a tough choice for a person, right? That's why we argued that this should be done transparently to the programmer, user, etc. Okay, but this was, I believe, a good step in the right direction. Except DRAM manufacturers said, we solved the problem with DDR4, and everybody stopped doing memory controller solutions. And we'll talk about that. Okay. So, okay, this is an example of a slightly intelligent controller, in my opinion. It's basically understands in a probabilistic manner, something is going on and does some refresh. And I think we need much more of that. I should here mention that we haven't been actually building flash memory controllers. This is our infrastructure for flash memory. It's a FPGA-based infrastructure where we actually understood a lot of the error mechanisms in flash, and we wrote papers about it. I'm not going to talk about that. But flash memory has the read disturbance problem much, much worse than DRAM. We wrote papers in 2012 that say read disturbance is going to be an even bigger issue in flash memory. But what saves flash memory storage is you have a controller that's sitting in front of the storage, correcting a lot of these errors. You can actually do a lot of error correction mechanisms over there, a lot of room for creativity, except flash memory is very slow. I believe DRAM needs to go there also. We need a DRAM translation layer at some point, except we need to be very, very careful with how we design that DRAM translation layer. Okay. So before I go into a little bit more history, I should say that I think today we need to understand even more than before because this problem has become much worse. There are many effects that still need to be rigorously examined, like aging. This is something we're working on right now, environmental conditions, memory access patterns, etc. And I think we need to design efficient and more principled solutions to the problem, and I'm going to talk about that. So there's a lot more research that's going on in this direction. I should also say that it's not just about RowHammer. There are other Bitflips that we're going to talk about as well. Okay, now let me give you the history of it. So DRAM manufacturers said, okay, we solved this problem. And to our surprise, everybody believed them. And nobody, essentially people stopped building these memory controllers. I think Intel could have built a much better memory controller, for example. So we actually questioned this in academia. And we said, is this really true? And we questioned in two different ways. One is device level. Is this problem really easily solvable as it's claimed? And we also questioned in a different way, system level. Meaning, okay, there are these solutions that are out there, DRAM chips that are claimed to be RowHammer free, can we actually break them? Can we actually induce Bitflips in them? I'm going to give you the device level first because I think device level is very fundamental. It's always good to start from the device level. So we revisited RowHammer. This is a paper that we wrote in ISCA 2020, 6 years later, our original paper. And basically, we studied many more chips this time. I'll give you the high level. I won't go into detail because we don't have a lot of time. But essentially, we found out that newer DRAM chips are much more vulnerable to RowHammer. The number of hammers to induce a single bit flip reduced to 4,800, more than an order of magnitude, essentially. And you get more bit flips and more rows farther away from the victim row. And existing mitigation mechanisms are not going to scale, essentially. So if someone claims that they've solved the problem, they actually had a lot of effort into this problem, and they either knowledge that nobody knew about, or they had very good creativity. Okay, so these are the chips. Actually, we did a scaling study, meaning we actually studied DDR3, DDR4, LPDDR4, and a lot of chips, a lot of infrastructure. We built actually very special infrastructure for this. It took a lot of time. And this is, let me just give you one example over here. Essentially, all DDR4 chips, the curve looks like this. New DDR chips, the curve looks like this. What is the curve? The curve is hammer count. If you go going from right to left, hammer count reduces to induce a bit flip. And the y-axis shows the bit flip rate, essentially error rate. And going from bottom top, error rate increases. So going from DDR4 old, both the hammer count reduces and bit flip rate increases, meaning chips become much more vulnerable. Okay. This is the solution study that we did. Basically, unfortunately, the axis is kind of different here. This is hammer count over here. Going from left to right, hammer count reduces. And this is the performance overhead of the solution. Higher is better. Lower means that you lose more performance, it's normalized performance. And these are real data points from DDR, LPDDR. You can see that we're marching from left to right. And the solutions become much worse as you march from left to right. This is para, the solution that we thought was good. If your RowHammer threshold is 1,000, which is today, you lose a lot of performance with para. Increasing the refresh rate is actually much worse over here, as you can see. So there's no solution that we knew of at the time. Even the ideal solution loses performance, although for some definition of ideal, I'd be happy to talk about that. Okay, we said that this is a very tough problem to solve. People should be investing a lot more into it. And then we actually wanted to characterize RowHammer. I'll go through, yes, please. So 1,000 within a refresh interval. Yes. So within today's refresh intervals are 64 milliseconds. Actually, today is 32 milliseconds. It's marching down. Just to give you the perspective, you could, with today's row trove activation delays, you could put 1.3 million activations within a refresh interval, and you could target them to the same row. So if you want, you can put many, many more of those thousands within a refresh interval. And okay, I should also say that I think we're marching from left to right. People are actually putting device level solutions, because I think this has slowed down a little bit. But imagine a world where you could actually induce these bit flips after 100 activations. Actually, existing workloads do that. Many existing workloads do that. So existing benign workloads can start inducing these bit flips. And that's a dangerous thing, I think. Okay, so we built more infrastructure to study the characteristics of RowHammer. This is a paper that we published in 2021. We wanted to understand the effect of temperature, aggressive row active time, and physical location. I will not go into a lot of detail over here because I'll talk about this one a lot more later on. This led us to find out something really, really interesting. You may think temperature is interesting. Unfortunately, we didn't find any good temperature effect on RowHammer. Basically, different cells are vulnerable at different temperature ranges to RowHammer. And this is also what makes it, one of the reasons why this is the case is because this is a very different failure mechanism than we see in retention. And certain physical regions of the DRAM module is actually a lot more vulnerable. If you know this, you can actually design a better defense or a better attack. So all of these actually can be useful for attackers as well as the defenders, depending on which hat you put on. So I think everybody should invest in understanding more. If you're an attacker, you should understand more. Okay, so let me give you an example over here. Actually, I will use this example because I'm going to get back to this later on. So for example, this is what we found. In most DRAM chips, 10% of the DRAM is much more vulnerable than the remaining 90% of the DRAM. Remaining 90% DRAM is 2x less vulnerable, let's say. If you actually know which rows are more vulnerable, you could tune the aggressiveness of your defense mechanisms so that they're much more efficient. You see that we see significant area reductions in defense mechanisms. I'll talk about defense mechanisms a little bit more. It turns out it's not as easy to do. We have a paper at HPC 2024 that talks about the spatial variation and a lot of interesting things over here. I'm going to skip some of these, sorry, but I'd be happy to talk about these. There's a lot of information here. So word line voltage, Iris asked this earlier. Essentially, there's no silver bullet in voltage, unfortunately. We expand our infrastructure so that we could actually change the voltage at plus minus 1 millivolt levels. And this is what we found essentially. If you reduce the voltage, you can actually reduce the RowHammer vulnerability, that's correct, but you cannot get rid of it completely. You can see that numbers are relatively small in terms of how you reduce. Unfortunately, reducing the voltage increases the row activation latency, and also it reduces the data retention time. This is actually a slide that I like because this is the pain of DRAM manufacturers. When you're manufacturing DRAM, you may say, okay, manufacturers did not do a good job. I disagree actually. Even though I have a lot of qualms with DRAM manufacturers, they're doing a lot at this level to optimize DRAM. They have nowhere to escape because it's not an easy device level solution for them. It's not an easy circuit level solution for them. And they're experts at that level. They're doing a lot at that level. In the end, their trade-off space is very limited. That's why we need to bump this up to the system level so that the system can actually help their job a little bit more. Okay. So basically, there's no silver bullet over here. Whatever you play at the circuit level plays against something else that you want to optimize in memory, like latency or retention. Okay. So as I said, I will not go through this. Essentially, this happens in the HBM chips, and HBM chips are at least as vulnerable. And there's also other effects at HBM chips because of 3D stacking. HBM is 3D stacked memory. You have memory layers and a logic layer underneath or on the side. Essentially, we see very interesting effects, but I don't have time to cover that. One of the issues when you're doing studies in this, in RowHammer or this sort of thing is you're limited by the infrastructure that you can build. So for example, our HBM infrastructure is not state of the art, right? People are using HBM3 today, but we could actually do studies with HBM2. We can just project into HBM3. HBM3 is probably much, much worse than HBM2, basically, based on what we know. Okay, this is what I mentioned earlier that I'm not going to cover. Now let's talk about solutions. Any questions? Sorry,
Question.
Yes.
I'm backing up about a half an hour ago, sorry.
Don't worry, sorry.
Saying that, RowHammer is activating DRAM. DRAM is, lower level memory, main memory. I mean, why aren't we moving this data, the reads that you're doing to cache or at least, SRAM level?
Yeah.
Where you have the other problems, but at least you're not vulnerable.
Yeah. So SRAM has its own vulnerabilities. There are other read disturbance vulnerabilities, but it's much easier to protect against because it's on chip, and Intel, for example, or AMD, whoever is building the chip has full control. So the reason is you cannot have everything in SRAM.
Sure.
And if you're building an attack, you can bypass all of those. It's very easy to bypass.
But can't you detect just based on that? Why is it easy to bypass, right?
No.
Yes, there's non-cacheable data,
Sure.
but shouldn't that trigger some kind of alarm? Like, what's going on here? Why are you specifically
Accessing some.
writing to non-cacheable data?
So now you're getting into RowHammer solutions. Basically, you could potentially add stuff on the processor memory hierarchy, like caches, to identify what are you accessing a lot, right? I agree. I think there could be possibilities, and there are actually papers that have proposed that, very recently written in 2024. Can we augment the cache hierarchy a little bit to count the activations that are going on to particular places and do something about it? But I think that falls into very similar approaches. Like in the end, you need to have some access counter based mechanisms. But maybe you're envisioning something else that could be a solution. I don't know. Yes, please.
I'm going back 3 slides.
Okay. 3, I can go back, I think. Okay, fine. I don't need to. Yeah, go ahead. Okay. Yeah. Yeah, I mean, I'll essentially process manufacturing variation. So whenever you manufacture a device, especially at the very small scales that we're doing today, you get huge amounts of variation in the circuitry. This is true in any logic chip as well, right? Some parts of the logic chip, you cannot essentially operate at a very high frequency because they're more vulnerable to errors. It's the same effect, essentially. So the main reason is really random process variation. There's also some systematic process variation, but we couldn't see any effect of that in these studies so far. Although, talk to me later on because we're investigating that. Yes?
Do I need like cache management instructions in order to execute a RowHammer attack?
No.
No, so I can do it with like.
Yes, that's a great question. Basically, we wrote initially in our paper we use CL flushes, but you don't need that. People can actually build eviction sets, and a lot of attacks today in memory go through eviction sets. You can actually evict whatever you want from the cache. You can figure out what's going on in the cache.
You can do it fast.
You can do it fast enough, yes. Yes. It's beautiful. Security people are actually amazing in understanding the underlying hardware. Actually, Dirk did a lot of some earlier microarchitectural security works that I know of in 2002 or so. So he knows a lot about this stuff too. Okay, so now let me go into what we did at the system level. So DRAM manufacturers say we solved the problem. We said, okay, in ISCA 2020, concurrently with this work, it's very hard to solve the problem. But did you really solve the problem? So we bought the chips that the manufacturers said are RowHammer free. They actually really wrote RowHammer free. These are RowHammer free chips. We thought, okay, maybe they had a solution that looked like this. Essentially, if you will want people to pass, you build a fence, but if the fence is not good enough, then people still pass, right? Okay, so this is the first work. We called it trespass because TRR is the solution that was put into DDR4, target row refresh. DDR4 never explained how this works. They basically said, okay, something is happening, we're going to refresh target rows. They never used the word RowHammer. We're going to get back to that in 2023. And they basically, we hypothesized that internally in the DRAM chip, they had some sort of tables or some probabilistic mechanism. And these tables kept track of rows and they kept track of the activations of those rows. Eventually, this table had to be of limited size. We said that, oh, if we could figure out the size of this table, maybe we could actually craft a pattern of attack or number of activations to different rows that could overflow these tables. And that's the idea over here. Using our FPGA-based infrastructure, we hammered many rows to bypass these internal proprietary tables that are supposed to be detecting the aggressor rows. And to be able to do that, we had to reverse engineer using, and here we had to use our FPGA-based infrastructure. It's very difficult to do this at a system level. And we actually provide an automatic tool that can effectively bypass these protection mechanisms. There are better tools right now. Okay. So this is an example. So this is a three-sided attack. This is double-sided. You have three aggressor rows, and you have more victim rows, as you can see. This is a four-sided attack. You have four aggressor rows. So if you're keeping track of only two aggressor rows internally inside the DRAM chip, these will bypass both of those protection mechanisms, right? And we actually saw real bitflips. These are real bitflips from real DRAM modules. In some modules, you get bitflips after hammering 5 different aggressor rows. Here, 7 different aggressor rows. Here, 9 different aggressor rows, depending on what's internally there. And we didn't have to reverse engineer completely at the time, although today we can reverse engineer almost completely. You can see that we tested about 42 modules. In 1/3 of them, we were able to induce bitflips. And we basically declared victory at this point because we were able to show all DRAM manufacturers are vulnerable to this effect, again, even though they claim these are RowHammer free. Yes.
This is sort of like an indirect attack on the table. Would it be possible to attack the table directly since we were able to figure out where it was?
We're not able to figure out what it was. So the table itself, that's a very good question. Table itself is not made of DRAM. It's SRAM internally inside the DRAM chip. So it's a lot less vulnerable to that attack. But yes, if you could actually induce bitflips in that table, you could probably do even worse things. Yeah. Okay. So we actually went and worked with the security researchers to show that you could actually take over phones with these attacks. These are some phones, as you can see, where we were able to find patterns. And there are different types of attacks. Some of them are actually taking over the machine. Some of them are actually finding your keys. Some of them are different attacks. But we were able to induce different attacks at relatively quick times, even though these were RowHammer free chips. Okay, that's the key results. So basically, we said that RowHammer is still an open problem, and security by obscurity is likely not a good solution, because this is what the DRAM manufacturers resorted to, right? And still what we're resorting to right now at this point in the industry. I'm going to tell you the more recent solutions soon. Unfortunately, we need to get out of this mindset, in my opinion. Okay, so these two papers together cause a lot of churn in industry. And especially hyperscalers like Microsoft and Google pushed manufacturers to do something about it. So people in JEDEC is the industry standards body that determines DRAM standards. They actually released 2 white papers in 2020, 2021. And more recently, they've done something else. This is the DDR5 standard updated that has an even more aggressive RowHammer solution. But I'm going to talk about that in a little bit. Any questions? How well are we doing on time? 10 minutes, really? Wow. Okay. I have 100 slides for 10 minutes. Okay, I'll speed up. So basically, you can reverse engineer everything. This paper shows that the solutions are very poor. We have a methodology for this. You can actually download it and do it yourself. Essentially, we were able to reverse engineer almost everything that's going on internally inside the DRAM chips, which is fascinating. And if we can do that with academic budget, if someone who's a lot more motivated can do it a lot better, in my opinion. Okay, ECC doesn't work. You can actually induce many more bit flips, up to 7 bit flips in a code word. Okay, so other people are also studying this problem. Google actually introduced this beautiful attack. I will mention this because I think this is very important for building solutions. These folks show that you can actually hammer this aggressor row A a lot, and then hammer this aggressor row B a little bit, and then you get bit flips in victim row C. Now, this sounds interesting, but the reason why this is interesting is because of the solutions. If you hammer this aggressor row A many times, internally the solution will refresh aggressor row B, meaning that you would activate aggressor row B using refresh. The solution itself can become an attack on the victim row. So you've got to be extra careful with the solutions as well in the end. And they publish this at User Security. People have been publishing solutions. I will not go into this in a lot of detail, but for example, this is another solution that doesn't scale to RowHammer counts of hundreds. It works with RowHammer counts of 1,000, but if you go to 100 or 10, this solution doesn't scale, meaning its overheads become very high. Even though I believe actually it's a step in the right direction. The idea is we didn't want to change DRAM, we didn't want to change, and we want it to be scalable. And if you don't want to change DRAM, one way of actually doing this or solving the problem is identify which rows are being attacked and stop accessing them, as opposed to refreshing the victim rows. Refreshing the victim rows require knowledge about the DRAM internals. If you throttle access to the aggressor row, you know which one's the aggressor row, don't access it. And I like this solution because we also use Bloom filters, which is actually nice hardware structures over here. And we show that this is actually pretty good at the time, but today, again, it doesn't work. But now you can see that this is a more intelligent controller, right? We're not talking about probabilistic. Now we're talking about Bloom filters in the memory, etc. And I believe we need more of this. So let's get back to these solutions. I think we need to have a lot more efficient solutions. So what did the industry do? I think industry is finally at a better point, meaning they're talking about RowHammer. This is a paper at ISSCC 2023. It's from SK Hynix. They talk about RowHammer. As you can see, you can find it here somewhere. Essentially, they said that, and they're more careful. And they have intelligent memory controllers inside the DRAM chip. So what was the solution that they proposed, which is actually adopted by JEDEC right now? The idea is, this is a solution that we discussed in our original paper, and we dismissed as being too costly. I still don't think this is the best solution, but it's good that people are actually looking into it. So the idea is basically for every DRAM row, they have a counting row, meaning a counter associated with every DRAM row. And they don't talk about how they exactly do it, but they increment the counter by some amount every time you activate it. And at some point, if the counter is greater than a threshold, internally DRAM takes some mitigating action. Now you can see that there's some control inside the DRAM, right? Which is, if you actually talked about this and went into a DRAM manufacturer 10 years ago, they would kick you out of the room for saying this. Now they're implementing it. That's good. Now, there are a lot of questions over here. How do you set the counters? I mean, how do you increment the counters? How do you decide when to take a mitigating action, and what kind of mitigating action do you take? All of these are extremely important, actually, for both correctness as well as performance and energy, and they don't talk about any of this. So there's still a lot of obscurity going on. So of course, because SK Hynix published a paper, Samsung had to write their own paper. Terrible paper, very hard to read. But I mean, at least they wrote a paper talking about RowHammer. That's good. Microsoft has been developing a lot of interesting solutions. It's a beautiful paper that's actually predates SK Hynix paper that talks about essentially counters per row, which is interesting. And eventually this went into JEDEC standard right now that talks about it, at least in some fashion, while skirting around these really, really important issues of how do you actually deal with the counters. Okay, now let me back up what I just said. How do you increment the counters is actually an important issue. And we keep asking this question, are we now RowHammer free? And the answer is I don't believe so. And we have a lot of other issues to deal with. There's a paper that we published last year at ISCA. We call it RowPress. Let me give you the key idea. Well, it's different from RowHammer, basically. But it can work together with RowHammer to amplify these bit flips. It's essentially a different read disturbance mechanism. And there's a paper that's coming up at the International Reliability Physics Symposium soon that talks about why it's building on our work. They basically show that this is a different mechanism at the DRAM level. We show that it's different. And we actually build a user level program that induces bit flips on RowHammer protected chips differently from trespass. And we provide some solutions. So what's the idea? Essentially, the idea is very simple. You activate the DRAM row, keep it open for a long time, and you get bit flips in the end. So you don't need to hammer it basically many times. And they don't require many activations. In extreme cases that are not allowed by the standard, only one activation induces bit flips. This is very fascinating to me, actually. So basically, this is the question we asked. I'll show you this. But basically, the issue is a lot of these solutions require counting activations and taking some mitigating actions. So if you set your counter value to some value, and if you're able to reduce the activation count that induces a bit flip, your solutions are essentially useless at that point, right? So this is what a classical RowHammer attack is like. You keep the row open as little as possible, and you keep activating. You need a lot of activations for that. But if you keep the row open a little bit longer, this is allowed by the DRAM standard, by the way, you can actually reduce the activation count by about 9x over here in this particular case. Now, if you configured your RowHammer threshold to be, I don't know, even 15,000, we will be able to bypass it with this. Okay, so we're using our FPGA-based infrastructure, and now we don't hide the names of the manufacturers anymore because it's very well known. At some point, they deserted, I think. I'm just kidding, of course. I think security folks have a different mindset. Security folks always give the names of the manufacturers, right? Whereas as you go toward the manufacturing side, you try hiding stuff. And there are a lot of good reasons for that also, but there are a lot of bad reasons for that also. And I'm happy to talk about that too. So basically, RowPress significantly amplifies DRAMs vulnerable to read disturbance, and it has a different underlying error mechanism from RowHammer. Let me give you the key result. This is basically based on testing of real DRAM chips. This is RowHammer. You keep the row open as little as possible, dictated by the standard. You keep the row open a little bit longer. 70.2 microseconds is allowed in today's DRAM standard. You get 1 to 2 orders of magnitude reduction in the number of activations that are needed to code the bit flip. This is violating the DRAM standard, 30 milliseconds. Nobody keeps the row open that long today. But if you do it at the device level, you'll get a bit flip with only single activation. You don't need to do any RowHammer at all. Okay, so why is this different? Because this is actually very much correlated to temperature. As temperature increases, this becomes worse. And also, different set of cells are affected, and it's based differently based on access pattern, et cetera. And we have a lot of detail in the paper. Now, building on this, we said that we could actually induce this bit flip in real processors, and we built a program. So what real processors do is, in the memory controller, they keep the row open longer if you actually keep accessing cache lines in the same row to take advantage of the row buffer locality. And we basically wrote a program that exercises essentially. And if you keep accessing the row, for example, 32 cache blocks, you start getting bit flips. And this is real results from real Intel chips. So one solution, you may say, don't keep the row open, right? Keep the row closed and pre-charge it as quickly as possible. That's very bad for performance in many applications because you don't exploit the row buffer locality in DRAM. Okay, so what do the mitigations look like? So essentially, as the row open time increases, the activation count to induce a RowHammer bit flip or a bit flip reduces. And identify this curve, and you can identify this curve through profiling. Limit the maximum row open time. In the end, I think you have to limit it a little bit, but limit it such that you don't lose huge amount of performance at least, and change your RowHammer configuration such that you start essentially you start taking a mitigating action at a lower activation count. That's the idea over here. Not as easy as this figure shows. And once you do that, you lose a little bit more performance in the end. Okay. Okay, there's a lot more in the paper that I'm not going to talk about. But basically, this is what I meant by, okay, how do you increment the counter? When do you decide to actually take a mitigating action? And I believe there's more to come. In my opinion, we're just scratching the surface. DRAM is going to get much worse. And any scaled memory technology also is going to get much worse, in my opinion. Okay, we have 2 minutes. So I will mention this. I've already said this, but maybe I'll skip a lot of these. There are a lot of interesting things over here. I'm going to skip some of these bit flips also in the bridges. This is actually in Pittsburgh, where I used to teach. This is the Forbes Avenue Bridge, and it collapsed because of another reliability problem and also negligence. But yeah. Okay. Let me give you some final thoughts very quickly. I think I'll conclude very quickly, but I have to mention this because I think this is fascinating. There are a lot of people who worked on security that knew bit flips were bad. We're not the first one. I've never claimed that we're the first one. In fact, people who worked on cryptography were probably the earliest ones. They said, if you get a fault attack, all bets are off, basically. You will lose your keys and all of this is useless. But I like this paper specifically. This was published in 2003 in Oakland, IEEE Security and Privacy. These folks from Princeton, they basically said, if you are able to induce bit flips in memory, we could take over your Java virtual machine. This is very similar to the Google's RowHammer attack on the native client, Google native client. And how do they induce Bitflips? Well, physical fault injection. I think basically they put a lamp next to memory and they got a lot of errors. Now, this is not very easily controllable, of course, clearly, but they were able to actually induce this attack. This is very fascinating to me. And even though this paper is, I think, great and very reasonably cited, it did not really take the security community up in arms about developing this sort of attacks because you needed this access, right? So what RowHammer did, in my opinion, is basically replace that lamp with software. Essentially, now you can induce these bit flips much more predictably using software and user-level software. Okay, as a result, that's why people are writing about it, and that's why I think security community looked a lot more into the hardware security after this. Okay, I will skip this. I think I'll mention this part. Bad news, I think this is going to get worse. And it's not just RowHammer. I think we're going to see a lot more of these bit flip issues in DRAM and other memories. Good news is hopefully we're at a better place. Although I'm not sure if the industry mindset is best still. I think we need to change that mindset a little bit more. At least in academia, people are doing a lot of work on understanding as well as attacks and defenses. I believe we need more principled models and methodologies and solutions. And this is where we argue for memory controller system and memory cooperation. I don't believe hiding all of the solution inside the memory is a good solution. So that's what we're trying to do again, right? With the per row activation counters, for example. I don't believe that's going to work very well. It's going to, in fact, we have a paper coming up that shows that it has a lot of overhead, etc. It's going to appear at DRAMsec in June. And other people are also, I think, looking into it. So maybe we're back to square two in RowHammer because we're not at square one. At least DRAM manufacturers are not claiming that we've solved the problem. Okay, I should mention these are the people who actually did the work. I will flash some of their pictures. And if you're interested in getting into this area, we have a lot of open source things. That's how Google actually developed their attack, building on our own code. But if you're interested, we open sourced a lot of our simulators and infrastructure, and we'd be happy to help. And we have also courses online that you can read about. Thank you. I'd be happy to take more questions. Yep.
So a system level defense would be to reflect when you're starting to have an attack, have the operating system begin to moderate a process running on a core. But I'm assuming that you can get many cores cooperating at the same time since it's a DRAM and not a core-specific resource.
Absolutely, yes.
So has anybody explored that trade-off, and at what point is it that it doesn't become, like, could you do that in a browser using lots of JavaScript on lots of tabs concurrently, for example?
Like, could you do this attack on a browser? Is that, or defense?
Across multiple cores that would defeat a system level.
I see, yeah. So I think that's a great question. I have not seen any work that looks at a coordinated attack across different cores, but I have not seen a lot of work on the defense system level throttling also. I think you're proposing a system level throttling mechanism, right? Yeah, I think the performance implications of that system level throttling is very large. That's one of the reasons why people have not looked at it as much. People have looked at using performance counters to throttle an application, and they saw large performance overheads. Yeah. Now we should start throttling a core. I believe you can actually do that. I think coordinated attacks are possible in DRAM. That's what the GPU work did.
It's a deliberate attack versus an inadvertent attack.
Yeah. I think the problem is today we're at a point, deliberate and inadvertent is a bit nebulous because of the number of activations that are induced, that are required to induce a bit flip have reduced so much. Okay, I'll let you moderate.
With the like end of Moore's law, how worse do you see this? Like how many transistors will be put, the number of transistors we can put on the chip that will stop becoming limited. So like when you say worse, like in 10 years, would this still be a problem?
Well, I think it will be okay, unless we move to another technology that is less vulnerable, or someone figures out another DRAM substrate, and people are actually looking into it that is less vulnerable. I think it's going to get much worse because these interference effects are become much worse. Now, how much transistors do you dedicate to solve the problem? I think we need to have more. And in fact, the slides I skipped are basically saying we're going to see more of these issues. We're going to see them even worse. So we should really design our memory controllers to be much more patchable, flexible in the field. Because if we discover an issue like this that we didn't envision, and there's DRAM in the field, there's DRAM in space, in much, much harsher environments than we're used to dealing with here, can we actually fix that problem in the field, right? And if our memory controllers are as rigid as they are today, including the DDR5 spec that I showed you that does per row activation counters, you have no choice, basically. You increase your memory refresh rates, and that may not be great. If we have a more programmable memory controller, where we can actually update the firmware so that you could actually implement different types of solutions for different types of problems, I think we have a lot more chance to survive in space, for example, right? So I think we need to put more transistors into it. And we have a lot of transistors, in my opinion. I don't think, even with Moore's law reducing or slowing down, we have a lot more transistors. Yes.
So have you seen like an accidental RowHammer attack in the wild where like basically there's a benign program that effectively induces RowHammer?
Okay, so I'll give, now you're getting into stories, interesting stories. So I should also mention that Microsoft has a paper in ISCA 2021. What did they call it? It's about coherence, but basically they were able to induce these bitflips by inducing coherence actions. And these coherence actions led to activations, etc. Sorry, I missed. Basically, Kevin Lowland is the first author. He was at the University of Michigan, and Microsoft authors like Stefan Saroya is there. I would recommend looking into that. Basically, they showed that you could actually induce these bitflips in real programs. Now, industry actually, the way RowHammer was figured out, we actually spent a lot of time together with Intel to understand what's going on. But there were benign applications that actually induced this problem first. We were not the first ones to really discover it. It was really discovered in industry. What happened was, it was a program that, actually, there's a nice DRAMsec keynote, maybe I should mention that. That was last year, delivered by a principal engineer at Intel. He was not the one who discovered that, but he was exposed to some of these things like we were exposed to. Basically, it's a very similar mechanism like the coherence paper at Microsoft. And Moisey Prime, yes, Moisey Prime, that's right, sorry. It slipped me. Moisey Prime is the name of the paper. But basically, it was discovered in the field because a program was causing these activations because multiple processors were actually trying to access an uncacheable block. And they were actually hammering the DRAM using many row activations. It's very hard to see, but people actually found that. Now, how prevalent it is in current DRAM, I don't know, because there's more protection in current DRAM. So it's very hard to, in my opinion, current DRAM, it's very hard to induce bitflips accidentally because there is protection today, right? We had to bypass it, as you can see. But if you are willing and determined, it's a lot easier. But again, I'm happy to be proven corrected. Someone can show that maybe there's a program that does it because there's so many programs in the world, right? Yes.
Maybe this comes back to devoting more transistors to the memory controller. Do you see high-speed inline memory encryption and signing as part of the solution?
Yeah, I mean, that's a great question. Memory encryption. Memory encryption may not be easy. You cannot decrypt, right? If you get a bitflip, you will not get correct decryption. So you will detect it in some way. I think that's part of potential solution. People have been looking at integrity checking mechanisms also. And I believe that's part of the solution also. Even though these are high overhead mechanisms, they can play to be part of the solution. Because, for example, you may not be able to set these thresholds correctly. You need to have a backup mechanism to detect these errors in the end. And that may be a high overhead in terms of performance, as long as you don't do it always, right? If you do it a very small fraction of the time, and you can cache the errors that are not caught by some of these more quicker detection mechanisms, I think those are actually good mechanisms to look at. Yes?
For a tangential question, but back in the 80s, when I was paying attention to memory testing, they had these patterns developing ones and zeros and whatever.
Yes. March tests.
Right. Marching, developing, whatever.
Yeah.
The back then it was already known that there was a problem with scaling because there were not linear size test patterns.
Yes.
And past that, everything will be followed.
Yeah.
But I would imagine that those tests would be, very much in line with the detecting strategy. How has this field evolved?
Yeah, that's a wonderful question. I mean, I can give you my perspective. People were doing some disturbance testing early on. In fact, we talked with some of the earliest designers of memory at Intel. They had some of these disturbance issues and they had to deal with it somehow. Unfortunately, at some point, I think maybe they didn't do these hammer tests as much, right? So what happened was, and the issue is, we also looked at how can we actually fix this problem with testing. It's extremely costly tests. So you need to do hammerings of all rows, hundred thousands of times to be able to discover it purely by testing. And I don't think testing was as rigorous. You're absolutely right. If you do enough testing, you should be able to detect this. You need to do hammering of all rows enough times, right? I don't think they did it. Now, should they have done it? I think that's a different question that we can discuss maybe over years. But what happened was actually the first people who picked up on our paper was not Google. It was really the memory testers. This Passmark software, they actually do the MemTest 86. They basically read our paper, they developed a hammer test, and they actually put it on our website. You could download it. It was not a perfect hammer test because it's not easy, because you need to test. There's also the data pattern issue, right? You need to test the different data patterns to find the problem. But if the DRAM manufacturers know what they're doing, they should find the worst case data pattern for their own system. But from outside, it's a bit harder. So what they did was they actually released this hammer test. And apparently, this is still on their website, I believe. They started getting calls from many customers saying, oh, I'm getting errors in this hammer test in all of our modules. Why? And they had to write on their website saying that, look, this is a known problem, read this paper. So they point to our paper. So I think for some reason or other, these tests were abandoned. I believe the main reason is cost in the end. These are very costly tests. Mark tests are less costly because you don't need to do activations many times, but we talk with a lot of testing people as well, and we try to develop testing. In the end, it becomes extremely costly to figure out.
Back then was a 4K bits per module. And
Yeah, exactly. Yeah, I think maybe, so what we've argued, actually for other reasons as well, not just RowHammer, is to do some of this testing online, meaning you have an intelligent memory controller, and online you keep testing. And I think this is really necessary going forward, because what happens is in our very recent papers at HPCA, we showed that your threshold, RowHammer threshold, reduces by about 6-7% if you keep hammering rows. So aging has an effect. And if you actually set your threshold with static testing before manufacturing, you may have a completely different dynamic picture 5 years down the road in a harsh environment, for example. So that we've always argued for online profiling as part of the intelligent memory controllers. But I think testing is an important component of that intelligent memory controller.
thank you.
Thank you.
Right. Is there any other questions? We're over time. Okay, let's thank Onur again.
Thank you.